I thank the organizer for the invitation. I think it's my first presentation in this series of workshops. So it was also an opportunity to see old friends in Pisa, a person that I didn't know since, I didn't see in a long time. So I've seen that in this session, you hear a lot about non-additive systems, in particular systems with long-range interactions. So I hope that this sort of my contribution will be a sort of introductory contribution. It's the work of a series of people, but in particular of this guy, Ivan Latella, who now unfortunately got a position in Barcelona as a permanent researcher, and Alessandro Campa, Lapo Casetti, Agustin Gonzalez, Miguel Rubí, and Pier Francesco Di Cinto. It's a collaboration that started in 2015, and we have a series of papers. The last one appeared in JSTAT-MEC in 2022. So this is just to give you that it's a lot of work we have done. So it starts from the consideration that, try to keep the 20 minutes, that non-additivity is a property of long-range interactions. And usually when you do thermodynamics, you impose additivity in order to get all what you want. So but I think that I didn't realize, and it was in fact the important contribution of the Spanish group of Ivan Latella, was the fact that the non-additivity implies also a violation of some thermodynamic identities. One which is very important is the violation of the Gibbs-Duhem relation. And the violation of the Gibbs-Duhem relation implies that there should be a consequence in the theory of ensembles. And this is the thing that the Spanish group had not done. In fact, the change is that one has to introduce a new ensemble that didn't exist before. So we have called it, we have given it the name of the unconstrained ensemble. The unconstrained ensemble, if you have only one substance, is an ensemble where the number of particles, the volume, and the energy fluctuate all together. Now, there is a very famous work, a paper by Guggenheim in the 30s that essentially says that this ensemble has a zero probability. So the thermodynamic potential that have this ensemble is identically zero. So why? Why? Because the system are there is an hypothesis, and the hypothesis is that the system is additive. If the system is non-additive, it is possible to have this ensemble. Now, then this was first discussed by a very famous person, but not, I think, not enough known in our field, which is Terrell Hill. Terrell Hill, in fact, discusses this ensemble when discussing finite systems. So he calls this the subdivision potential. So the fact that you can split the system in many parts, and the cost of splitting the system is expressed by this extra energy that is the potential of this ensemble. So I realize that I don't have enough time to enter in all these. It's a lot of work. So maybe I will give a few formulas. Recently in Florence, I did the blackboard. So I don't know if I will go at the blackboard at some point to explain, because some of the formulas are sort of tricky. So, but we wanted to give an example, and the example is, in fact, we took from a very famous model by Tiring. I will show you what it is, this model, at some point. And in this model, we had formulated, and I think from the from the point of view of teaching ensemble inequivalence, this model is very fit for this type of. It's a very extremely simple model. This is another concept on which I worked in a non-additive system, that the ensembles are not equivalent. Don't give equivalent predictions. In particular, phase diagrams in different ensembles can be different. And since we now introduce another ensemble, you expect that also in this case it will give different predictions if the system is non-additive. And we have modified the model in order to get phase transition. It was not easy. I think that it will be possible in the future to devise models, more realistic models. But for the moment, we sticking to the theory model. In order to have phase transition in the unconstrained ensemble, it was necessary to introduce repulsive interactions, which were not present in the theory model. Theory model was devised for self-gravitating system, so it is intrinsically an attractive model. And in order to have phase transition, we have to add some aspect of repulsion that was not present in the model. So, but I think in the future it will be possible to do more in this direction. Okay, so so where does the Gibbs to Ham? By the way, I would like to recall here, since I'm in Pisa, one of the two characters that make the Gibbs to Ham relation. One is Gibbs, that everybody knows, and the other one is Duhem, that maybe you don't know. Duhem, just a few words, since it's a very interdisciplinary workshop. So he was denying the scientific revolution. So he was saying that Galileo gave no contribution, in fact, and he was supporting the scholastic and for instance, saying that William of Ockham essentially discovered everything about science. Another thing that he was a very conservative Catholic and traditional person. And also another thing that is important is the Duhem-Quine hypothesis. The Duhem-Quine hypothesis says that you cannot falsify a theory. So if you have an experiment that says something against a set of hypotheses, the fact that the experiment doesn't turn out right it is not a deny of the theory. It's a deny of one of the hypotheses of the theory. So you never know which of the hypotheses. And since there are also hidden hypotheses, so this is the type of logical reasoning that was very interesting. Besides that, so he was really a strong scientist, and he was opposing atomism, for instance. He was one of the first enemies of Boltzmann. So he's not the kind of guys with whom I would have to have a relation. So he was not a simple person. So, but anyway, okay, he did something important in the particular. By the way, this Gibbs-Duhem relation, I think, you know, things acquire a name essentially by chance. So it's not difficult to derive it. It's here. So. And it says that if you take a system with a certain number of parts, a certain volume, and certain entropy, there is a relation between the differential of the chemical potential, the differential of the pressure, and the differential of the temperature. And you know, so this shows that chemical potential cannot be independent from pressure and temperature. So, by the way, this when I knew, in fact, I remember when I saw this thing, I remember that I knew this fact because for me, the chemical potential has always been a very mysterious potential. So this is a way of understanding the chemical potential, because then you put it in relation with pressure and temperature, which are very much more visible things for me. So okay. So I remember I read it maybe in some old book. Zemansky, there is something like that. Okay, where does this relation come from? In fact, it comes from the homogeneity of energy. Energy, so this is why at some, this derivation, in this derivation you have you start from a relation which is called the Euler equation, not because Euler was particularly related with this relation again, but because Euler studied a lot homogeneous functions. So when you start from this type of relation, which says that the energy is homogeneous, the homogeneity factor lambda, you arrive very easily to this property. It's a two-step derivation. You find it in Cullen book, for instance. You derive this relation with respect to lambda, and then you put lambda equal 1, and you get this relation, which is called the Euler equation. Then you differentiate this relation. I'm doing a lecture in thermodynamics, I realize, okay. You differentiate this relation, and then you apply the first and second principle, which is what, when I was a student, was called the TDS equations. So there is an equation which summarizes the first and second, and you get this relation here, which implies the Gibbs line. So it's a very simple derivation starting from homogeneity. What happens if the system is non-homogeneous, so it's not additive? So for instance, you might think that this is very strange, but this is very broad audience, so I start with a very simple example. If you take the simplest model of a ferromagnetism from any book, which is the Curie-Weiss model, it's an example of a system which is non-additive, although you will never find this comment in the books. Why? Because suppose I have a state of zero magnetization, and I split the state into two parts with positive and negative magnetization. Of course, since the energy is the magnetization square, the magnetization square of the total is 0, but the magnetization square of each part is not 0. Okay, so the energy of the total is not the energy of the parts. And so if this is true, it's impossible to have the Euler equation. So this is a system for which Gibbs M will not be valid, because, at least could be valid, but it cannot be derived from the homogeneity assumption, because the homogeneity assumption is not valid for this system. Now, fortunately, there are no consequences of this non-additivity. Fortunately, I mean for Kerson Wang, who wrote a book in statistical mechanics and discussed this model. And there is no mistake in his book. And the reason is that the phase transition of this model is second order. But as soon as you have a model with first order phase transition, which is the Tiering model, for instance, the fact that the system is non-additive has consequences. And I have 6 minutes now. And as consequences, and for instance, the one first consequence that we discovered together with David Mukamel and Julien Barré more than 20 years ago, that the ensembles are non-equivalent. So, for instance, the result in the microcanonical ensemble do not coincide with the result in the canonical ensemble. So you have to solve the two ensembles together. There is no problem. So I remember that when we first found this thing, the people were asking, what do we do if the ensembles are non-equivalent? There is, in fact, no problem, because the ensemble describes different physical situations. So there are situations in which the system is isolated, and you will treat it with the microcanonical ensemble. There are situations in which the system is in contact with the heat path, and you will treat it with the canonical ensemble. And in general, if the system is non-additive, you might expect that now there are a lot of systems for which this ensemble inequivalence has been studied. Self-gravitating system, Coulomb and dipolar system, two-dimensional fluids. So there are a lot of systems now, and we also wrote a book about that years ago, together with Duccio Fanelli and Thierry Doxois, where we discuss all these ensembles. For instance, recent, just to quote, in the field of self-gravitating system, recently there is a study of Scott Reman, who is a very well-known astrophysicist in Princeton, of the matter near black hole in the center of the galaxy, and there are phase transitions that are not equivalent in the two ensembles. Just because of the non-additive nature of gravity. Also, a very important part of this field is the systems that are small with big S. This allows me to remember a person that was very influential on me. Was Dieter Gross, nuclear physicist from Anne Meitner Institute in Berlin, who died unfortunately. And he was studying, for instance, phenomena in nuclei that are small systems, and he was discovering several aspects of ensemble inequivalence. So non-additive interaction lead to ensemble inequivalence, and different ensembles, different properties, and there are implications like, for instance, negative specific heat and other features. Now, I realize that it will be impossible for me to enter in details, so I will sketch the ensemble story just to give you. So essentially, what one has to do the statistical mechanics of corresponding to the violation of the Gibbs 2M, one has to generalize the distribution function of the Gibbs ensemble, if you want, of the Gibbs grand canonical ensemble. So you see here there is a multiplier for the number of particles. The distribution is an exponential. There is a multiplier for the energy, and there is a multiplier for the volume. So there are three multipliers: one for the number, one for the energy, and one for the volume. And now it's a question of you can derive very easily, although, okay, you have to do it, that if you take, this is the normalization, okay, you sum over all the energy levels, over all the volume, all the particles, and this is the potential, gamma. It's very simple to show, and this was in the paper of Guggenheim, that this is zero if the system is additive. So this is a proper thing, but it is not zero if the system is non-additive. And okay, how to derive thermodynamic relations? This is something I discovered in a paper that I didn't know before. So essentially what you do, you take the differential of the energy in terms of the differential of the probability. And if you do this, it's a two-step derivation. You arrive at the thermodynamic relations of this kind, okay, which is very much of the type, you see, you define the entropy, and okay, you have the thermodynamic relations of this kind with three multipliers. And then what you do, you define another. So you see, Euler relation will be this one equals zero. But in this setting, since I have three multipliers, the left part of this relation is not zero. Is this function epsilon, which has to be computed. And of course, then once you have this function, you have the usual thing. So you can derive, say, entropy in this ensemble by taking the differential of this function with respect to t, with respect to v, and with respect to. Okay, I have finished my time, so I think okay. Okay. So just to give you the. Just. I don't have a slide with the. I would like to just tell you what is the model in boards. So you take a box. Sorry. You take a box of volume V, and then you take another box of volume V0. It's a very simple model. In fact, I think it should be used to teach several of these things. And then you have particles, and particles rebounds on the walls of this larger volume. But when they are both inside of there are two particles, at least two particles inside the small volume V0, they get an energy minus epsilon, so they fall into a constant potential. This is what is the Thierry model. So okay, so what we had to do in order to get phase transitions in this new setting, we had to add a repulsion. So the particles that are outside this volume, they repel. So you have to push the particle inside the smaller volume in order to have, this is technical, we believe. So at some point we will get a better model to get phase transition in this new ensemble. But this, for instance, is an example of this model, the phase diagram of this model. This parameter eta was introduced by Tiering, is essentially the log of the ratio of the two volumes, log of V0 over V over V0, and this is temperature. And this, in the canonical ensemble, you have a line of first order phase transition that ends on a second order critical point. While in the microcanonical, you don't have a line, you have a sort of forbidden region, so there are no states inside this region. And you see that the critical point is totally different from the one in the canonical ensemble. So the phase diagram is completely different in the two ensemble for this very simple model. It's a paper by Tiering of the 1970. It's very simple to read. And it's, I think, so what we added, this is a paper by us, is a complete study of the model for all set of parameters and discovered this different way of putting the system. Okay, so I think I will finish here. If there are questions.
One quick question.
Paolo. I have to say that I'm very much impressed by your talk. It is extremely attractive. I have two comments. A question is, did you write, do you plan to write a book, a new book on statistical physics? Because if you do, I will adopt that for my course of statistical mechanics, statistical physics, which is impressive. I'm very impressed. Then I have a question, another question, that a conjecture. See, you have been talking about what you call crucial events. I wonder if your approach to statistical physics might be the foundation for what you call crucial processes, crucial events, which is that a conjecture that I don't know. But anyway, I'm very much impressed.
So I must say, I first heard about crucial events yesterday, so I should study them. So I will look into detail. So for the moment, of course, this is all about equilibrium. So there is nothing which is out of equilibrium. So, but I think that the next step will be to study non-equilibrium in these conditions, and this will maybe to dynamics and things like that. Wonderful. So about writing a book, in fact, last week we had a meeting for the 70th anniversary of Roberto Livi, and Angelo Baracca came to the meeting, and he was sitting on the first row. And I told him, look, we should write together a new chapter in your book of statistical mechanics. So maybe, I don't know if the book can be extended to this new part. My friends in Florence, Lapo Casetti, teaches part of this story to students in StatMech in Florence. So he devotes one lecture or two, because it's really something which is, I can give you a paper that a student, master student from Barcelona wrote, just thought for teaching to master students, which is essentially the use of the four operations, so there is not much in the derivations, so for the Tiering model. So you are right, it's so simple that one should know, very basic courses.